An exoplanet is a planet that orbits a star other than the Sun. Currently, more than 300 exoplanets are known. Most were detected by astronomers who measured the back-and-forth wobble of the central star as it dances around in its orbit with the unseen planet. Of these 300 exoplanets, a small number, only 42, are viewed edge-on, meaning that the tilt of their orbit happens to bring the planet in front of its parent star once each orbit. This event is called a transit. When it occurs, we are granted unprecedented access to the physical properties of the planet. In particular, we can determine two key properties of the planet. First, by measuring the amount of starlight blocked by the planet as it passes in front of the star, we can estimate the diameter of the planet. Second, by observing the size of the back-and-forth wobble of the central star due to the orbiting planet, we can directly determine the mass of the planet. More massive planets exert a bigger tug on their stars, causing a bigger wobble of the star. Once we've determined the mass and diameter of the planet, we can calculate its average density and therefore make a first guess at its composition. A low density would imply a gaseous planet, similar to Jupiter, whereas a high density might imply the planet was made of rock and is similar to the Earth. Since low-density planets are larger in diameter, they block out more starlight when they pass in front of their stars, and hence they are easier to detect. It's no surprise, then, that for the past 9 years, astronomers hunting exoplanets have studied only gas giants similar to Jupiter. In this tour, we will survey several of the transiting planets, beginning with the first such object, HD 209458b. This planet was first detected by the back-and-forth wobble method of the central star, which revealed the presence of an unseen planet with a mass 70% that of Jupiter orbiting. Surprisingly, this planet was much closer to its star than even Mercury is to the Sun. The planet only took 3.5 days to orbit its star. Because the planet was so close to the star, there was a 10% chance that it would pass in front of its star from our point of view, and indeed brightness measurements in 1999 proved that this was the case. Although the mass of the planet was much less than that of Jupiter, the diameter turned out to be 30% larger, so its density was much less than that of any body in the solar system. The underlying cause of the puffy nature of this planet remains a mystery. Unlike the planet we just discussed, most eclipsing planets were not discovered by measuring the back-and-forth wobble of their stars, but rather by surveys that search for the dimming of stars as their planets pass in front once per orbit. We will now take a look at the results from one such survey, the Transatlantic Exoplanet Survey, or TRACE for short. TRACE used a network of tiny 4-inch telescopes that stared at large patches of the night sky, night after night for several months at a time. Computer software analyzed the thousands of images gathered for each patch of sky, measuring the brightness of about 20,000 stars in each image. Most of the stars are quite boring. They don't vary in brightness. However, a very small fraction of stars have planets with orbits tilted just right to bring the planet in front of the star. By sifting through the data, the TRACE survey succeeded in its quest to identify several needles in the haystack. They found 4 eclipsing planets. The first planet found by the TRACE survey was inventively named TRACE-1. Although TRACE-1 is similar in diameter to Jupiter, its parent star is much smaller, cooler, and redder than our own Sun. Follow-up studies of TRACE-1 with the NASA Spitzer Space Telescope yielded the first direct detection of light from an exoplanet. Since Spitzer is able to directly measure the heat of the planet, astronomers were able for the first time to determine directly the temperature of a planet orbiting another star. This planet proves to be a scorching hot world, as expected from its tight orbit around its star. The second planet, TRACE-2, is special since it happens to fall in the field of view of the upcoming NASA Kepler mission, which will launch in March of 2009. Free from the effects of the Earth's atmosphere, Kepler will be able to search for very small changes in the brightness of these stars. By studying TRACE-2, Kepler might be able to detect rocky moons or Saturn-like rings orbiting the planet, or even find smaller, rocky planets that orbit the same star. The third planet found by TRACE, TRACE-3, is notable for its very short year. The planet takes a mere 31 hours to complete one orbit around its parent star. Due to its proximity to the star, TRACE-3 is expected to be extremely hot, with an exotic atmospheric chemistry unlike anything in the solar system. The most recent planet found by TRACE, TRACE-4, has proven to be a real puzzle. Its density is only 1/6 that of Jupiter, much lower than any object in the solar system, and similar to the density of Cork. The large mass of TRACE-4 should make the planet contract under its own gravity, so the fact that the planet hasn't done so is a conundrum. With the discovery of dozens of gas giant planets, scientists are refining their methods to find smaller rocky planets similar to the Earth. Finding such planets is difficult, of course, since the area of the Earth is less than 1/100th that of Jupiter. A first step in this direction occurred in 2007 with the detection of eclipses of the planet orbiting the star GJ 436. This planet is much less massive than Jupiter, yet much more massive than the Earth. Indeed, it is quite similar in mass and diameter to our own Neptune. Like Neptune, the density of the planet orbiting GJ 436 is high enough that we know it must be mostly made of ice and rock, and not gas. With the launch of the Kepler mission in March 2009, we will undertake for the first time in human history the hunt for true analogues of the Earth, small rocky planets at just the right distance from the Sun to allow liquid water and possibly life on the surface. Kepler can accomplish this feat because it can both measure very small changes in the brightness of stars, and because it can observe a very large number of stars, more than 100,000, continuously for 4 years. Since Earth-like planets only pass in front of their stars once per year, it takes several years of data to catch them. By the end of its mission, Kepler will have answered one of the great questions in astronomy. Are planets like the Earth a commonplace throughout the galaxy, or are we a cosmic rarity?